You have stuff for me too? Al? There were two clear, obvious places where people got booted in the head. What is the definition of a multiplicative inverse? We used it in a whole day talking about solving simultaneous linear consequences. That whole section with the Chinese remainder theorem. Some of you had it written on your formula sheets and still didn't fill in the answer to the question. That was the most blank question on this exam. And the recursion proof by induction seemed to be less than ideal. So I'm going to say this, and hopefully you understand. You will see these things again. This is comparable to the drop I have seen on this exam every semester. These topics are always one of the hardest sets we do. But none of you are in a position where this is unrecoverable. So if you have questions about your exam grade or your grade overall, come talk to me. Be glad to talk to you about it. Meanwhile, I want to continue our discussion on recurrence relations. So we were talking about how one creates and then works towards a closed form in a recurrence. We had the Fibonacci example, we had the Tower of Hanoi example, and I ended the class on Friday with the following question. And I said on Friday that this was going to take a while. So here's where we start taking a while. I need to say that the techniques for solving recurrence relations vary dramatically based on the recurrence itself. So I'm going to limit the type of recurrences I'm looking at to start. I can then generalize substantially, but we'll start with what I think are the easiest cases. This is where we're going to start. There's a bunch of words in here that I don't know what the meaning of them are in this context. So, recurrence relation. Linear. What's a linear equation? Algebra question. Not a discrete question. It's the algebra question. What's linear mean in this term? Yeah. Straight line. So what's the equation of straight line look like? You all get an F in algebra. No. That's just a particular straight line, right? In general. Okay. Or I could take that and I could put all the variables on one side, right? Number x plus number y equals number. So we can think of linear as somehow being related to the idea of using a straight line. But in calculus, we start talking about polynomials. We start talking about degree. See the word degree here. What's a linear polynomial? Calculus, stuff where the variables in the first power. Quadratic is squared, cubic is third. So I'm thinking here again, if a, b, and c are constants, x and y are the variables, they're to the first power. I don't have an x times a y in this problem. Then that would be a power of 2, wouldn't it? One of the x's, one of the y's. Like I was mixing my powers. I'm going to consider linear here to be the idea that the pieces in my sequence, pieces in my recurrence, are all first power, maybe times a coefficient, the numbers a and b. Aha. So linear, constant coefficient, these ideas go together. So I'm thinking of something where I have my nth term, an. Like we did back in chapter 2, I'm going to define this in terms of the previous ones. Subscripts here are just placekeepers. Hey, wait a minute, I see a K here. K. We called this something on Friday. We didn't call it degree. Called it something else. Call it on Friday. Depth. So I think of my degree here as the depth idea. This goes back K terms. So the degree here is the same as our depth idea. Constant coefficients means that all of these CIs are real numbers. And I want to make absolutely sure, in order for this depth to actually matter, I need to make sure that CK is not 0. Ugh. There's one other word up there in that description that we haven't defined yet. What's that word? Still don't have any idea what it means. Say again? Homo. Oh, geez, that does look like an R. That should be an S. Homogeneous. Yeah, okay. Homogeneous. Wait a minute. Homogeneous. I'm going to go back to my Latin study. Greek studies. What's homo mean? Same. Same what? Genius. Homogeneous. Same gene, type, variety, same idea, same thing. Okay. All of these pieces are the same. They all involve a number and a term of the series. AN has the number 1 in front of it. The rest of them have some other constant. What's not here that we've seen in other recurrence relations? Think of our Tower of Hanoi relationship. What's your Tower of Hanoi relationship? HN equals -1. 2 HN minus 1 plus 1. 1 didn't have a term of the series in it, did it? It's just the number 1 all alone. Okay. I remember on the exam, the second exam with chapter 2 in it, right? We had a sequence in that one. I asked you to find terms of a recurrent sequence. What's the recurrence relationship from that? Go grab your copy of exam 2. What was the recurrence relation for the question in exam 2? I believe it's question 4. AN equals.
AN minus 1 plus N times AN minus 2.
What kind of a coefficient is that? Sure as hell isn't a constant, is it? This is not covered by the techniques I'm going to do today. Our Tower of Hanoi. That doesn't look like the other term. There's no thing about H there. It's a constant, but there's no H part. That's not homogeneous. So I'm looking for recurrences that only look like this, like our Fibonacci recurrence. All of the coefficients are 1, but that's fine. This relationship well, you might say, hey, wait a minute, that's got a constant coefficient, right? But it's not linear. There's a square in there. So I'm really looking at a very restrictive set of equations. I'm looking at equations that are linear, homogeneous, constant coefficients. Degree, depth, whatever. This one, for example, is degree 2. Okay, so I'm restricted on what kinds of things I can solve. I'm going to use, in specific, the Fibonacci one as an example, but then I'm going to generalize. How do I solve these things? This is my generalized version of the thing I'm trying to solve. I want to know how to come up with the answer to this thing. I'm going to make an assumption. Ian, when we solved the Tower of Hanoi problem, what did we end up with? But that closed form looked like what? And then we converted it to be one solution, didn't we, right? But that series was what kind of a series? This is the word I'm looking for. A geometric series. Geometric series are powers of something, right? So I'm going to make an assumption. I'm going to assume AN is some power like a geometric thing. It's a geometric idea. And then I'm going to try and figure out what possible values for R will work. So if I do this, then I can plug that in here. No, wait a minute. If AN is R to the N, then this side is R to the N. This is C1 R to the N minus 1. This is C2 R to the N minus 2. All the way down to CK R to the N minus K. Dr. Sassmore, this is still effing ugly. Yes, it is. I'm about to make it nicer. There's a common factor of a power of R here. These powers are going down as I go from left to right. So this is the smallest power of R. I'm going to divide by that power. Divide by R to the N minus K. Okay, wait a minute. When you take one power of X and divide it by another power of X, what do you do with powers? I subtract. Well, wait a minute. I'm dividing this by that. What do I get? I get R to the 0, which is 1. So over here on this end, I now just have CK. What do I get when I do this? I'm going to have to subtract N minus 2 minus N minus K. What happens to the N's? They cancel. So I have negative 2 minus K. Negative 2 plus K. What happens when I do this one? Aha. Hey, wait a minute. Put it all on one side. That's R to the K. R to the K minus C1, R to the K minus 1 minus C2, R to the K minus 2 minus CK equals 0. What do I have? I have a polynomial. In the variable R, not the variable X. But that's an equation, right? It's an equation of degree K. Now I know what I called it. Depth became degree, because this is an equation of degree K. I'm going to call this the characteristic relationship, the characteristic equation. And now I can use this to find values for R that work in my recurrence. All I have to do is solve this problem. Sure. All I have to do is solve this. Yeah, sounds like a piece of cake. Everything I'm going to do here today is going to be based off the idea that we start with a degree 2. I can make it as general as we want, but we're going to start small. This is going to be my example problem to start with. Notice that I have added the initial conditions here. And I've got my recurrence. Give me the characteristic equation for this recurrence. You'd end up with a quadratic equation whose variable is r. I replace the an with r to that power. I then divide by the smallest power. Put it all on one side. And I get r squared minus 4 equals 0. So far, so good? What are the roots of that equation? Solve that for r. Aha. Here is the best part. Those are the two numbers that I am allowed to use for r. But if I can use each of those numbers, I can use any combination of those two numbers. I now can guarantee that the solution I want looks like this. Sure it does. Well, if I take that and put it back in here, what's negative 2 squared? What's positive 2 squared? 4, right? So if I put n minus 2, I would have taken off 2 of them, right? That's taking out a 4. There's the 4 right there. That's exactly the piece I need to make this work. This is the first big result for recurrence relations. The roots of my characteristic polynomial tell me what an looks like. Now I just have to figure out what alpha 1 and alpha 2 are. What's the one piece of information you were given in this problem that I have yet to touch? My starting values. If this is the right format for an, then it should work when n is 0. It should work when n is 1. All right, we had A0 was 0, and we had A1 was 4. Well, that means that n is 0 here. What happens when you put 0 into this equation? Because anything raised to the 0 power is 1. What happens when you put in n equals 1? Alpha 1, 2 to the 1, plus alpha 2, negative 2 to the 1, gives me 2 alpha 1 minus 2 alpha 2. You now have simultaneous equations. I'm going back to the algebra I took before calculus. Solve those for alpha 1 and alpha 2. You can do the method of substitution. You can do elimination by addition. You could make a matrix and plug that matrix into your calculator and do its reduced row echelon form, or any other version of solving simultaneous equation that you know how to do. I multiply the top equation by 2. I get 2 alpha 1 plus 2 alpha 2 is still 2 times 0 is 0. Bottom equation does not change. Add those together. Elimination by addition. 4 alpha 1 equals 4. So alpha 1 must be 1. If that's the case, what's alpha 2? Take that, put it back in, solve. I now know what my AN should look like. AN should be alpha 1 times 2 to the n plus alpha 2 times negative 2 to the n. I've built the whole sequence. That's the answer. That's an explicit closed form. If I want the 100th term, what do? Plug it in as 100 and walk away. You don't have to do the recurrence anymore. We made it work. This works every time when we have two solutions to our equation. As long as I can find the roots of my equation, this works. Try it again. Here's a new problem. Let's go to town. Characteristic equation. What's the polynomial we end up with? Divide everything by r to the n minus 2. That makes this r squared, this r to the first, and this r to the 0. Put it all on one side. And I get this quadratic. R squared minus 5r plus 6 is 0. What are my roots? I have two distinct real solutions. Great. R1 and R2. I don't care which is which. The only thing that's going to change, if you put them in a different order than I do, is which thing you call alpha 1 and which thing you call alpha 2. Nothing else will change. You will end up with the same answer. It just might be in the other order. So, those are my two values. That means that an should be some number times 3 to the n plus some number times 2 to the n. And if you put them in the other order, big deal. How do I find alpha 1 and alpha 2? Use those starting conditions we were given. If n is 0, I have A0 equals 1. That means I get A0 equals alpha 1 times 3 to the 0. That's just 1. Alpha 2 times 2 to the 0. That's just 1. A1 is 0. So 0 is equal to alpha 1 times 3 to the 1. Plus alpha 2 times 2 to the 1. Solve for alpha 1 and alpha 2. Take that value, plug it back into this equation. So an is -2 times 3 to the n plus 3 times 2 to the n. Ta-da! Ready for the sneaky one? Here's my buddy Fibonacci. I said if I want to know what happened at the end of the year, I was going to have to do all 12 of the numbers. If I want to know what happened at the end of 2 years, I had to go to 24 months. No. I want you to solve, at least get the roots. What's going on? What's the polynomial for this one? Please notice, I know this is going to be degree 2. It only goes back 2 steps. Rather than put in r to the n, I know that the highest power I'm going to end up with is r squared. So I could just say, oh, r squared equals r plus 1. Going down by the power, starting at 2, going down 1, going down 2. Putting the coefficients 1 and 1. You could do the r to the n and then divide by the lowest power. If I move it all to one side, r squared minus r minus 1 equals 0. Who's taken their artistic expression course already? This expression right here. This expression shows up in classical art. I'm talking about particular shapes. Shows up in Greek architecture, Roman architecture, shows up in Da Vinci, in the Renaissance. It's everywhere. The hell is so important about this damn thing? I'll get back to it. What are the solutions to that? What are the values for r? I put in -1, -1 squared is 1. 1 minus -1 is 1 plus 1 minus 1, that's 1, not 0. This doesn't factor. What do I do when it doesn't factor? X is equal to -b plus or minus the square root of b squared minus 4ac all over 2. Can't get that stupid tune out of my head. All right, but A, B, and C are all either 1 or -1. X equals -1 plus or minus -1 squared minus 4 times A, 1, C, -1 over 2 times A, which is 1. Negative and negative becomes a positive. 1, -1 squared is 1. Subtracting a negative, that becomes addition. Square root of 5 over 2. Wait a minute. So that means my numbers are those two numbers. That number has a name. You should Google that. The golden ratio. In art classes, a rectangle is perfectly proportioned if its length to width ratio is that number. Statuary, the front of the Parthenon, the size of the buildings, the front of the Lincoln Memorial, the size of the White House, they're all dictated by that number. So I know that AN is equal to alpha 1, 1 plus square root 5 over 2 to the nth power, plus alpha 2, 1 minus root 5 over 2 to the nth power. How do I find alpha 1 and alpha 2 again? I use my starting conditions. F. This was F, not A. Fn, Fibonacci. F0 was 0. F1 was 1. I'm going to save you some trouble. It takes a bit of work. On page 544. Which means I have a formula for Fibonacci numbers. The nth Fibonacci number is 1 over the square root of 5 times the quantity 1 plus root 5 over 2 to the nth minus 1 over square root of 5, 1 minus root 5 over 2 to the nth. Fibonacci was counting rabbits. I don't know what the hell square root of 5 has to do with these rabbits. But that is amazing as all hell. I can't even get, I don't even know why you would put in n and be guaranteed to get a whole number out of here, much less the whole numbers that follow this particular recurrence relation. This is amazing. By the way, 1843, guy by the name of Binet was the first one to write a paper about this using this method for solving linear recurrence. So this is commonly known as Binet's formula. But all it is the technique we just learned applied to a very particular example. Question. I don't want you to solve it. I just want you to get me the characteristic polynomial, characteristic equation, and the values for R. What happened? Houston, we have a problem. What problem? It's not distinct anymore. What do I do? Tune in next class. I'll see you all then. You have a wonderful rest of your day. If you didn't get me your homework, please bring it up. If you have any questions about your exam, I'd be glad to take them in discussion with you.